Thank you, Professor Shu, for inviting me to deliver a short talk at the Taipei Tech Penn State Joint Symposium. How marvelous to talk to two sets of colleagues simultaneously who are separated from each other by half the rotational period of our planet. I'm going to briefly present today some theoretical results on thin film solar cells that emerged during the last year. These results are quite relevant to the climate emergency that our civilization has begun to encounter. But first, let me recount two very happy visits that I had at Taipei Tech. The first was in 2009 when Professor Yijun Jen organized a mini symposium on sculptured thin films there. The second was in 2013 when I held an international chair professorship there. Both times were occasions for research discussions and collaboration with Professor Jin, which continue to this day. Returning to the main message of my talk today, let me begin by drawing your attention to the year 2019, which is the second warmest year on record. We know this very well at Penn State, as it is the home of some of the finest climatologists and meteorologists in the world. The year 2020 will rival 2019 once all the data have been processed. Not wishing to end up like fried eggs, I began to work on modeling solar cells about 10 years ago. Why solar cells? Well, all energy production must release greenhouse gases, which cause warming. But not all sources are equally bad in that respect. See the difference in greenhouse gas emissions from diverse energy sources. The emissions are mentioned here in tons of carbon dioxide equivalent due to the energy use of 160 people in the European Union. Coal, the number is 820 tons. Oil, 720 tons. Natural gas, 490 tons. Biomass, anywhere from 78 to 230 tons. Hydropower, 34 tons. Nuclear energy, 3 tons. Wind, 4 tons. Solar, 5 tons. Thus, fossil fuels release 100 to 160 times more greenhouse gases than solar photovoltaics. Electricity from solar cells and wind turbines has declined significantly in cost, especially solar, in the last 10 years. Coal has remained more or less steady. Nuclear has actually increased in cost. What about safety? Well, the death rate from accidents and air pollution is 1,000 times greater for coal and oil than for solar cells. Solar cells are thus a major candidate to help us ward off the worst effects of climate emergency. But photovoltaic solar cells are used to meet just 1% of the global energy demand. Even though rooftop solar cells are being deployed on large buildings as well as on single-family dwellings. And not to mention, big solar parks are being built. At Penn State, soon, about 25% of our electricity will come from solar cells. Important as solar parks are, they are not enough. What we need is ubiquitous generation of electricity integrated with devices. Each microgenerator should run off solar radiation and/or ambient light indoors. It should also be flexible and made of non-toxic, earth-abundant materials. Colored solar cells, which would be less efficient, would also fill a niche. Today, CIGS and CDT solar cells are the most common thin film solar cells, about 5% of the world market. CZTS, CZTSC, and gallium arsenide solar cells are also attractive. But gallium arsenide solar cells are primarily for non-terrestrial use because they are expensive. Indium is not abundant on Earth, and cadmium is toxic. But CIGS and CDTE are more efficient than CZTS and CZTSE. So we need to increase efficiency and reduce material use. These two objectives have guided my group's modeling research. A solar cell requires optical modeling as well as electrical modeling because it is an optical device as well as an electrical device. Optical modeling requires the solution of the wave equation, which is of the hyperbolic type. But electrical modeling, in contrast, involves the steady state diffusion equation and the Poisson equation, both of the elliptic type. Optics modelers generally try to enhance the photon absorption rate, that is, the electron-hole pair generation rate. But that is not enough, because there is electron-hole pair recombination as well that they do not take into account. Electrical modelers perform optical ray tracing and thus greatly trivialize optics. What is needed is an optoelectronic model with a rigorous photonic step and a rigorous electronic step. That is what we devised. The details were published last year. Briefly, we employed the transfer matrix method for the photonic step and the finite element method for the electronic step. We also used the differential evolution algorithm for optimization. I'm going to succinctly present theoretical results that we have obtained showing that single junction thin film solar cells with more than 30% efficiency are possible. This solar cell has a magnesium fluoride anti-reflection coating, an aluminum doped zinc oxide front contact, and an oxygen deficient zinc oxide front passivation layer. Then come an N-type cadmium sulfide layer, a P-type CIGS layer, and a P-type CZT SSE layer. These are the three main semiconductor layers, followed by an aluminum oxide back passivation layer and a molybdenum back contact. Note, there is only one NP junction, but the semiconductor structure is of the NPP type. The two P-type layers of CIGS and CZT SSE are the two photon-absorbing layers. Both P-type layers are compositionally graded so that the band gap energy varies along the thickness direction. We optimize the grading for highest efficiency. This is the optimal band gap profile. It is not constant through each of the two absorber layers. It has high gradients at the front and back faces of each absorber layer. These gradients create high drift fields to increase the open circuit voltage. The optimal bandgap grading also consists of a triangular region in the middle of each absorber layer. You can see them marked by stars, red stars. This middle region creates a high drift field that favors charge carrier collection deep inside the absorber layer. In at least half of each absorber layer, the band gap is uniform and low. This is good because then less energy is needed to excite an electron-hole pair across a band gap. This figure shows that, generally speaking, the electron-hole pair generation rate is higher than the recombination rate throughout the two absorber layers. The JV curve shows that the fill factor is 0.83, a high value. The open circuit voltage is slightly less than 1.1 volts. The short circuit current density is 38.1 milliamperes per square centimeter. Most importantly, the efficiency is 34.45%. This is a very promising result because the efficiency exceeds the threshold of 30%. That is considered the Rubicon for single junction solar cells. Crystalline silicon has an efficiency of 26.7%, perovskites 21.6%, and their tandems 29.1%. Gallium arsenide is the best thin film solar cell. With a constant band gap, the efficiency is 29.1%. SIGS has 23.3% and CDTE 21.0%. Since SIGS solar cells are fabricated on polymer substrates, the double absorber gradient band gap thin film solar cells can also be fabricated on polymer substrates. Thus, they should be flexible, rollable, and gluable. We are now in the process of finding experimentalists as our partners. Thank you for listening to me, Sheshe Dajia. I am now ready to take questions.